So we've looked at lots of different features of a variety of assembly languages and all the different ways these kind of decisions can be made. There's a few little features extra we're going to go through, and that should be the end of the set. So another big difference you have to decide on is how you're going to implement interrupts and traps. Whenever you're executing user code and you want to shift control over to system code, you have to decide how to do that. It can be very complicated, it can be very troubling, but the way you do this depends a lot on the way you implement branches, whether you need to store an internal control state or not. We'll get to that. So whenever you're going to stop user code midstream, you got to do a lot of stuff to make sure that the user code can be resumed uninterrupted, right? That the user code doesn't notice any changes. And so an interrupt often means you're going to shift a whole bunch of information around and then transfer control over to the system code. And the way to do that is tricky. You have to store the user's program counter, return address, stack pointer, any flags you might need. All that stuff has got to be stored somewhere. The machine's got to jump to an address specified by a trap vector usually. And then it may need access to specialized hardware, specialized privilege modes. So how does all that work? In LC3, this is a good example of a bad way to do it. Well, not a bad way to do it. I shouldn't say that. It's very fast and completely hidden because it is a separate part of the control system itself. So when you implement a trap or a system call, an interrupt, the control system, every time it starts a new instruction, it checks to see if a trap has been implemented, and then it'll go off and do this chain of instructions that shift registers around and reallocate the program counter, and then go back to the next fetch and execute. So it's like instructions within instructions. It's not quite microcode. It's like a micro control system between the microcode. It's really kind of weird. But that's one way to do it. It's very, very fast. It's completely hidden, but it's not extensible and it's not really pipelinable. So most modern systems don't really do that. Most modern systems have a couple of different things that we can handle. Traps and interrupts. Exceptions are when you load an instruction and then it can't execute that instruction. It's not an encoded instruction. But traps are when you tell the operating system to do something from your code. And interrupts are where something external tells your machine to do something. So we'll look at the traps first because interrupts are done the same way, more or less, with just an external signal. When you call a trap, you need to tell the operating system what you want to do, and then somehow the address of that trap vector needs to be found. Some systems will have the trap vector address be found by the operating system, and you just tell the operating system what you want to do, and it does it. Other systems will allow you to encode the address of your trap vector in the instruction itself. And so this is sort of a different decision. The privilege modes that get activated when you're doing a trap, there's all sorts of complexities, and we probably won't get into all of it, but you might have like protected memory mapping. You might have input-output that is mapped to memory locations, and you don't want your user code to be able to access that, but you do want the system code to be able to access that. Right? Memory management unit configurations, kernel memory regions might be protected from user code but available to system code. These are the kind of things that exploits can take advantage of to be able to execute unsigned code on your system. So these things have to be developed very, very specially. Be very careful with the way that you allow access to these privileged modes. And the other thing is that it can take multiple instructions to transfer control to a trap handler, right? If you are trucking along in your user code and then a trap is executed, it might take few instructions to swap over the stack, swap over the program counter, stuff like that. That sequence should not be interrupted, right? So somewhere you've got to have a flag that says, I am currently transferring control from user code to system code. No interrupts are allowed during this transfer. So that's another thing that is available in privilege modes. You don't want your user to be able to set those don't interrupt me kind of flags because those can be abused. ARM does a really interesting thing here, is it actually implements banked registers. So this means you have your regular register file, and then you have a copy of some registers. You have a copy of the stack pointer, you have a copy of the link register, which is ARM's return address,
you have a copy of the program status register. This is all your flags and interrupt modes and stuff like that. And then, in fact, there's a special mode called Fast Interrupt, FIQ, that also banks a few general purpose registers. And so you can actually transfer control to the Fast Interrupt handler, and you know that you can access registers 8 through 14 without stepping on the user's data. You don't have to push it to the stack. You don't have to preserve it. You can just use those registers, and that can speed up operations in some circumstances. So it's really quite a dynamic interrupt handling system that has been implemented. And I won't go into any more detail about this, but recognize that there are all these different choices that have to be made when you're handling traps and interrupts. You also might want to think about the different arithmetic options you have when you're implementing your instruction set. For example, LC3 doesn't allow a subtract. Instead, what you have to do is change a value from positive to negative and then add. And of course, it doesn't implement a positive to negative. So you have to flip the bits manually, add 1 manually, and then add. That's an interesting design choice, right? I mean, yes, you can do it all in code, but there are some circumstances where you're going to want to do it on your machine instead of in code. And so most modern machines use a fairly comprehensive ALU that can do lots of different things. ARM, in fact, can do more things than most because, as I said before, it allows any operand, almost any operand, to be shifted. Which is a really neat feature that gives some strength and power to the ALU operations. So you can either have a simple set of ALU operations and then perhaps need more instructions, or a complicated set of ALU instructions and then save a few operations. What about argument passing to a stack, right? If you are calling a subroutine, you might think about how you're going to pass arguments to that subroutine. Most machines implement a stack, but some allow you to move arguments via registers, right? They have special registers that are, by convention, reserved for arguments and return values. MIPS does this, and RISC-V does this as well, right? How is the stack implemented? Is there a fixed register? Is it user accessible? All of these different kind of things are questions that you ask when you're designing an instruction set architecture. What about extensibility? Do you make the instruction set architecture easy to expand, or do you run out of instruction space, right? LC3 only has one opcode that's not implemented. So there's no space to expand, right? Whereas RISC-V has expansion built in by default. And that sort of brings us to our next and sort of last feature of instruction set architecture design, which is reverse compatibility. Right? How do you interact with previous versions of this instruction set architecture? And modern languages, especially like RISC-V, have forward compatibility built in. They assume that things are going to change over time, and so they build structures that allow the assembly language to be extended without sort of messing around with the base instruction set. Now, the sort of full other side of that is x86, which is an instruction set architecture that was developed in the 70s and we still use today, and you can tell, right? ARM, MIPS, and RISC-V are designed with forward compatibility. You can expand and extend these things, but x86 inherits decades of legacy features so that old code can run, which is nice, but then you're sort of chained to these old ways of doing things. A great example is segmented memory. This is a feature that still exists in x86 today, even though it's sort of pushed to the side, and I'll tell you why in a second or how. It is still there because it was necessary in the first versions of x86. x86 had a 20-bit address space, and it soon became clear that you were not going to have enough memory in a 20-bit address space. And so in subsequent versions of x86, they implemented what they called segmented memory. So you'd have a special set of registers whose whole job it was to store the address of the memory segment that you're working with. So you have a data segment, you have a code segment, you have a stack segment, and then a few extras that are added. E, F, and G are extra segments that the user or the programmer can use if they want to. And so every address, every memory access, you start with the address of the segment, and then you add the 20-bit address of the data you're interested in, and they overlap a little bit, and you use that to generate a 32-bit address. This is a very expensive and complicated process that was not needed as of like the 386 days, but it's still there because we have to maintain reverse compatibility. In fact, x86-64 forces CS, DS, SS, and ES to 0. So they're in the architecture, but they are forced to be useless. It's like an appendix. It's a vestige of a previous version. It's a snapshot into what it used to look like. And we need it for reverse compatibility, but it's just this extra baggage that would be better not to have. F and G are still used for kernel and thread local storage, and you need architecture and instruction sets to support these segments. x86 also implements string instructions. It also implements binary coded decimal rather than hexadecimal. Dedicated registers, right? The named registers are all still there, and you can still use AX and BX and CX and DX like we saw before, even though the register file is a general purpose register file. So this is the sort of the last philosophy of instruction set design to really consider is at what point do you continue to preserve your old ways of doing things, or at what point do you just break and start fresh and make something completely new so that you're not tied to legacy features and you can implement modern features at the expense of having to write all your code again from scratch. These are the interesting decisions that we have to make.